All right. So I want to go over this, use the worksheet, kind of teach you some Earth space science stuff. Okay. My assumption is that um, you've probably heard of like, hey, what causes the tides? Oh, it's the gravitational pull from the moon. Like that's what I was told, but that was the extent of it. And I was like, well, why does that work? It's just a gravitational pull. So here's the real answer. It is gravitational pull, but here's why that causes the tides. Um, this is not to scale. Okay. Now, there's a force of gravity on the moon from the Earth. There's force of gravity on the Earth from the moon. Okay. This isn't being pulled in because it's moving this way. Just like your tennis ball, you're pulling in on it, but it wasn't hitting you in the head because it was continuing to move, and its inertia wanted to keep going in a straight line path. Okay, that was uh, part C. Now, because of this, there's a bulge of water here because it's closer to the moon. You right with that? Okay. That's only part of the story. The second part is so the moon's going around like this, but because gravity is acting on the Earth as well, the Earth is also affected by it. So the Earth is doing a little of this thing. It's quite exaggerated, but the Earth has that type of motion. Okay, if you spun a water balloon that was like a ball, a sphere, it wouldn't stay in a sphere. It would elongate a little bit, become oblong. Does that make sense? Okay, because of its inertia. And so that's what causes the bulge on the other side of the Earth. So you get two bulges, one here, one there. Good with that? How often does a tide occur? High tide, low tide, high tide, low tide. How often? Two times a day. Okay. That is because the Earth rotates one whole time in 24 hours. Initially, let's just say you're standing over here. You're experiencing high tide. 6 hours later, you're not at a bulge, low tide. 12 hours, you're in a bulge again, high tide. And then on the backside of the Earth, low tide. That makes sense? So there you go. Someone asks you, hey, why is the tides? You can tell them more than just gravity from the moon. Okay. Um, Number two, that's the acceleration of gravity. That's why on videos of people walking on the moon, they're like bouncing. So, a popular question that comes up is like, how do we know the mass of the Earth? Like, just like NASA built this big bathroom scale, like, step over here, please. So here is how that was unfolded. Newton figured this out. That was his contribution. He knew that the gravitational force was proportional to m1 times m2 divided by the distance of separation squared. But he didn't know what would make that equal, what value to make it equivalent. Okay, so this was an unknown, and Newton didn't discover. Later on, I don't know how many years later, but a guy by the name of Brahe, the rich guy with the golden nose, back then, rich guys were the scientists because they didn't have to work and like, what am I going to do? Like, oh, I'm going to discover stuff. So, what he did is he built a balance. One side had a lead ball on it, the other side had a hand balance. He measured the weight of that lead ball. And then what he did was he built this ginormous lead boulder. So what else are you going to do with your money? And rolled that underneath that suspended lead ball. Because this was so massive, this actually caused a gravitational force to pull this down ever so slightly. Does that make sense how this is working? Okay. And so he added a little bit of mat or a little bit of weight on there to counterbalance that pull. Whatever that added, that was equal to the gravitational force between these two masses. So then he had that. He had the mass of one ball and two. He had the distance of separation between them. And all he was missing was G. Once they discovered G, then they turned their attention to the Earth, looking at an object like you on Earth. You know your force of gravity. You know your mass. They knew G. They knew the radius of the Earth. And all that was left was the mass of the Earth. So they calculated it that way. Once they figured out G, they could also figure out the mass of the sun. And then the mass of all the other planets. So once this happened, it was just like opening the planetary Christmas gift. Like, whoa, like just kind of like I'm making this up. Within a year, they knew all the masses of all the planets. Okay. Here's another side note. The Greeks knew the radius of the Earth way a long time ago through shadows and measuring angles, doing geometry. They figured out, they knew that the Earth was round, and they figured out to a reasonable degree the radius of the Earth. And then somehow through history, we forgot that. I mean, think of Christopher Columbus. Don't do that. You're going to sail off the Earth. The Earth is flat. Like, where did that knowledge go? Like, we knew the radius of the Earth. Like, we knew it was round, and we knew the radius of the Earth. And then somehow, over 1,000 years or something, we got dumber as a culture. And the Earth is flat. So when people joke about like, oh, the Earth is flat, I'm like, stop. Really, seriously, stop. Don't do that. Like, we could go back to that. No, I'm not kidding. Like, somehow we lost. Like, think about it. What was Christopher Columbus told? Don't do. You're insane. You're gonna fall off the Earth. Like, that was held by a lot of people. So anyway, just some trivia there. Okay. Um, so here's the sun, here's the earth. A black hole. Here's how, well, okay. Our sun is not massive enough to form a black hole at the end of its life. It takes a really big star. Stars, their fuel are like neutrons and protons coming together, fusion. It's a atomic reaction that releases a bunch of energy. Okay, this is the fuel that makes stars what they are. That's what they burn. Okay, is this fusion reaction. When all the subatomic particles have fused, that's when it runs out of fuel. If it's a really big star, they go through a process called a supernova, which is kind of like the star's last stand, like gonna like an huge explosion. And then you got all these molecules of heavier elements just kind of floating out there, and then they start to like come back together because of gravitational attraction, and there's nothing to hold them back out, and so that conglomeration becomes what causes a black hole. There's so much mass and it's so concentrated. We're not sure. Um, we've never seen what's in the middle there. We're assuming that it's so strong that atoms can't exist. Like it just crushes, like so densely packed that electrons can't orbit. They just well, never seen that. Um, so that's where black hole comes from. But to get in orbit, you need a certain speed. You need this to be a certain mass. So the mass of the star is still there. It's just concentrated. And r is the distance from the center of mass to the Earth. That didn't change either. So it'll continue that circular orbit. We'll all die because we kind of need the sun. We're just a frozen rock floating through space. But it'll still orbit. Like the center of the Milky Way galaxy is an enormous black hole. But we're just sitting out here orbiting around there. We're all right. Okay. Sound good for that? A little disconcerting, but it's all good. And then number 5, you got to watch that from the surface. Add the radius onto that. Okay. This is one point that we'll get there. This is one point we didn't get to yesterday. What happened? So we derived this expression yesterday. This is the speed needed to maintain a circular orbit. Well, what happens if a planet doesn't have that exact speed? Well, if it's slower than that, what it does is it does an ellipse. Here's a fact. All orbits are elliptical. A circle is a special case of an ellipse. Just like A square is a special case of a rectangle. Okay, so all orbits are elliptical with the sun at one of the foci. Okay, if it's too slow, oh wait a minute. So this is the Earth and this is the sun. What would the consequence of that be? You think global warming is an issue now? Okay, and if it's too slow, okay, but if somehow the ghost of the Earth could be whatever, it would still it's still in an elliptical path. Okay, if it's faster than that special speed, it's doing an ellipse as well. Okay, this would be pretty rough. Okay, it'd be frozen. This is one of the difficulties that living on Mars, would have to be dealt with because its orbit is more elliptical than the Earth's, and so there's a period of time it gets pretty colder. Okay, and if it's too fast, it follows the hyperbola path, like a hyperbolic path, not coming back. Yeah. Okay. Cool with that. All right. Okay. Apparent weight. So your bathroom scale is designed to measure how much you weigh. What's another name for weight? Force of gravity. Okay. Is it possible to make the bathroom scale read something different than what you actually weigh? You might have been yelled at by your mom, but like taking and like holding on the bathroom sink and like pulling it out, like, yeah, I'm a beast. Sorry, you guys didn't see that in there. Holding down on the bathroom sink, like yeah, or like pushing up, like oh, oh, so okay. Did you really change your weight? No. So what really is the bathroom scale measuring? Well, what? Not force of gravity, because that's actually how much you weigh. It is a force, normal force. It's how much the bathroom scale is pushing up on you to support your weight. Okay? It's reading the normal force. I'm going to call normal force your apparent weight. It's how heavy you think you feel. Okay? So in these questions, consider you standing on a bathroom scale. So I'm going to ask for how heavy do you feel like you weigh. That's apparent weight. Think normal force. Think bathroom scale reading. Tell your neighbor. Everybody go to a C. Got a force of gravity, normal force. You're at rest, some of the forces are equal to 0. Normal force is equal to force of gravity. This is how bathroom scales are designed to work. Okay, but now let's change the scenario. Let's say that you are now speeding up, going downward. Tell your neighbor. Okay, correct answer is B. You are experiencing acceleration downward. You're not going to change the force of gravity on you. But in order to have acceleration downward, your normal force has to decrease. The floor is supporting you less. Does everybody know that feeling? Like, okay, you feel lighter. You all right with that? Like making that a connection between your personal experience and physics terminologies. Okay, you decreased your apparent weight. Tell your neighbor. Correct answer is C. You're moving at a constant velocity. Sum of the forces are equal to 0. Force of gravity is equal to normal force. So when the elevator levels out, like goes at a constant speed, you should feel normal. Now it's as it goes down, it's slowing down as you approach the bottom. Correct answer is A. You're experiencing acceleration upward. You're slowing down while moving downward. So you have to have, so the ground has to exert more force to slow your inertia down. You feel heavier. Good with that? You have more apparent weight. Tell your neighbor. How much is the floor supporting you? It's not supporting you at all. You feel weightless. Okay? So, drawing from your experience in an amusement park where they have the tower ride, where they lift you up and they drop you, that's what weightlessness feels like. Okay? You still weigh something, but your apparent weight is 0. There's nothing supporting you. You're like, okay? That's weightlessness. That's what weightlessness feels like. You all right with that? Okay.
The plane climbs to 24,000 feet, in our case from the Gulf of Mexico, and goes into a series of parabolic arcs. The aircraft climbs at an extreme angle, 45 degrees. It feels like 1.8 Gs, nearly pinning passengers to the floor. And then at 34,000 feet, it begins to dive at an equally extreme angle for half a minute.
Okay. Assuming nobody's been on this, but you can draw from your experience on a roller coaster. Okay? I'm not talking about the initial hill, but as you're coming up out of the initial hill, you're moving really fast and you're like, right? Like you feel heavier as you're coming up because you're experiencing acceleration towards the center of the circular path. Your normal force is more, your apparent weight is greater. That was the 1.8 Gs pinning them to the floor. Okay, but then it goes over the top, and it's just like going over a bump or a hill on a roller coaster. That feeling. Okay, and they're just doing that a whole bunch of times. So, Apollo 13 movie. This was made a while ago, but it was an astronaut movie, and they filmed it in one of these planes. Okay, so this is looking obviously out of the window at the plane. Notice, look how steep the angle is. Okay, right now it's like they're pulling up out of the initial hill on a roller coaster, like, oh, they're feeling really heavy. Okay, and then when they go over the top, just like on a roller coaster, you feel lighter. Okay, and that's inside, they're floating. Okay, so think if a roller coaster did that. It's called a vomit comet for obvious reasons. Um, so when you're on that drop zone amusement park ride, you're falling inside the ride. Here, they were falling inside the plane. So they looked like they were floating, but in reality, they're just falling. This is cool. You have a worksheet due on Friday. Okay, so notice sometimes the balls go down on the ground, sometimes they're floating. So this is where the plane's pulling up. Cool that.